Welcome back, everybody. So we're in the second part of the notes here on this second page. So we're going to be looking at vector subtraction as well as vectors in the coordinate plane. So note from last time, we kind of quickly discussed vector addition as being adding two vectors is going to represent the diagonal of a parallelogram. So I think I want to just jump into a quick example just to show why that is or how that works. So we're going to pick two vectors here, some relatively simple ones. We'll pick 2, 3 as our first vector, and then 4, 7 maybe as our second vector. So I'm going to draw my coordinate plane here. So for U, I'm going to use red, V, I'm going to use green. So U is going to be 2, 3, so that's going to be this vector here. And then V is going to be 4, 7. So that is going to be this vector here. Let's zoom in a little bit here just to focus in a little bit more on what the vector components are going to look like. So, oops. So if I'm adding these two vectors, again, what geometrically we looked at last time is that we're going to get a parallelogram's diagonal. So if we add the components of our two vectors here, what we're going to end up with is 6, 10. And so 6, 10 is going to be this vector from the origin to the end of the diagonal between the two vectors that we've created, so U and V in this case. And so the parallelogram is simply if we copied both vectors onto the heads of each one of the previous vectors from the origin. So again, not a super accurate picture here, but we'll see here that our new vector, U plus V, is 6, 10. So then the question is, well, what if I subtracted the vectors, right? So what if I had U minus V? Well, that would be U plus negative V. Oops, we don't need a question mark there. So U minus V is the same as U plus negative V. And so if you remember from last time, we talked about negative V being the vector in the opposite direction. So if we draw our V vector, so we'll note this is vector V, and this is vector U. What we're going to get for minus V is going to be this vector, but in the opposite direction. So 180-degree rotation from its current location. So, whoops. Let me try and draw that. Okay. So it's going to look something like that. And so if we kind of do our algebra here, so U plus negative V is going to be 2, 3 plus, now it's going to be negative 4, negative 7. So we're taking the opposite xy values here because we're going in the opposite direction. What we're going to get is negative 2, negative 4. All right, well, where's negative 2, negative 4? Negative 2, negative 4 is going to be here. So we end up with this vector here, which again is still just the sum of the two vectors. So I could again draw my two vectors as a parallelogram. And what we'll see that is not drawn to scale here is that this blue vector, which is u minus v, is actually the same as the opposite diagonal inside of our original picture. So again, not drawn to scale here, so it's a little bit hard to tell, but it is simply that length between the two vectors there. And that's what we see in our notes here. So in your notes in particular, you will see just this red line, which is that opposite diagonal. But we don't really need to think of it in this way necessarily if we're just doing the algebra. So just keep in mind you can just add the two vectors to get whichever diagonal it is going to end up being. But it is useful to think of the different directions in which vectors can be combined and what those parallelograms are going to look like. But the key idea is still that we're just going to add the components. So just below here, we're going to start getting into some examples just to work through some concrete examples that will allow us to create vectors and look at those two main components, which again are going to be magnitude and direction. So we're going to start with adding in our coordinate plane and then drawing a vector that is not at the origin. So we'll note a vector u has an initial point at 1, 3 and a terminal point at 4, 7. So maybe we'll add in some tick marks here. So our vector is at 1, 3 for its initial point or tail, and then 4, 7 for its terminal point. And so that is our vector u. So this vector is heading northeast at some angle measure, which we don't know. And so drawing it in the plane is useful. And what we can do from there, if we wanted to, is we could just draw it again at the origin. But we'd want to figure out, okay, well, what is u as a vector? So in other words, if I want u as those horizontal and vertical components, right, what should it be if it's not from the origin? So what we can do to start is simply draw a triangle from where it's located. So if I go from the head of the vector, I draw a perpendicular down to the distance where the initial point is located, and then draw a horizontal from there, connecting, we'll get a nice right triangle. And so we can see from our picture here that the distance along the horizontal is 3 units, and the distance along the vertical is 4 units. And these are going to be the two components for our vector. So u is 3, 4. There's one way that we could write it. The other way we can write it is using some engineering notation, which would be 3i plus 4j. And we'll see this a little bit in our homework. So I and j are going to be really important vectors for any of you planning on doing engineering courses. So I is what we call the unit vector in the horizontal direction, and j is what we call the unit vector in the vertical direction. So in other words, we can write a vector as a linear combination of a horizontal vector and a vertical vector. Okay. And note this would just be kind of the coordinate form here. And what we'll also note is that we can indicate the direction of this vector u as well, right? So theta is going to be the direction that the vector is moving in. So we can note that theta, if we want to calculate theta, given that we've got the opposite and adjacent sides, we can just use a little bit of inverse trig here. And we can see that arctan of 4/3 is going to be theta. And it's in the first quadrant, so not really much more work is going to be needed. Now the question is, what's the length or magnitude? So now we've got direction. So now what about length, right? How long is that vector? Well, we can kind of see that we've got a right triangle here. So the length is simply going to be found using the Pythagorean theorem. Right? So we've got a right triangle, and it's actually a really nice one because its horizontal and vertical legs are 3 and 4. So the length we're going to denote with absolute value symbols. Sometimes you'll see double absolute values or single absolute values. I'm going to use single absolute values. So the length is the absolute value of the vector, and that we're going to calculate using our distance formula. So it's going to be the square root of the sum of the squares, which is going to be, in this case, radical 25 or 5. So we can see here that our vector has length 5 and direction arctangent of 4/3. Now we'll probably want to calculate this, to get an actual measurement. We can measure it in radians or degrees. It'll kind of depend on the problem that we're working on. But this is going to be pretty much what a lot of the algebra is going to look like here. Breaking it down into component form, and then from there, finding the length and magnitude and direction. After we've found this vector, maybe combine 2 vectors together, combine 3 vectors or 4 vectors. As these vectors interact with each other through addition or subtraction, we can always recalculate what the new vector's angle and direction is going to be. Okay, so just below, we'll just kind of make a note here of kind of our general vector. So if I've got a vector u, I can fully describe that vector if I know x, y, and theta, where x and y are our component pieces of the vector, so the horizontal and vertical components, and then theta is the direction angle. So we'll start with magnitude, of course. So our magnitude is simply going to be the square root of the sum of the squares from the Pythagorean theorem. The component form of a vector is actually something that we're going to borrow from our trig functions section there. So if we think back to when we did the unit circle, we'll note the coordinate here, x comma y, that's the terminal point of our vector, can also be written using sines and cosines. So what we'll note here is that if we use sine and cosine, we can rewrite this vector as the magnitude of u cosine theta and the magnitude of u sine theta. And that is going to be because the magnitude of u is equal to the radius of the circle that point is describing. So there's a circle that we could draw there if we wanted to with radius r, and in this case the radius is going to be the magnitude of u. So we'll note component form of a vector can be written in terms of the magnitude and direction only. So note this component form is magnitude and direction only what's given. So theta is our angle for direction, and magnitude of u is our length or distance from the origin. But it can also simply be written as x comma y, or it can be written as x times I plus y times j for whatever x and y happen to be. So just note you're going to kind of see all three. And the one you'll probably see least is going to be this engineering notation with i's and j's, with the unit vectors. But still expect to see a little bit of all three. And then the direction of a vector, again, is that theta, which can always be found with the arctangent calculation of arctan y over x. And so these are going to be kind of the main pieces that we work with using trigonometry and a little bit of geometry with our calculation with vectors. All right, so if we pop down here, we've got a list of properties. These properties are extremely important in general, but for us, we're going to kind of focus on some that are going to be kind of the most commonly used types of things. So what we'll note here first is that we get nice properties of addition. So we have order doesn't matter when we add two vectors, so u plus v is equal to v plus u, and we can add them in any order. What I will note is the zero vector. So that's this 0 that is written in bold in your notes here. That is just the vector 0, 0, which is simply a single point. So it has no magnitude, has no real direction, but is a vector that will show up. A vector plus its opposite will be the zero vector. Multiplication by a scalar, again, the nice thing here is that the distributive property holds. So we'll be able to distribute scalar quantities. So what we'll note here is that C and D are scalars, which means they're just numbers, not vectors. Doesn't matter in which order that we add them either. And then our algebraic operations are really what we've already discussed. Right? So if we're adding two vectors, we will add the x and y components. If we're subtracting two vectors, we'll subtract the x and y components. And if I take a vector and multiply it by a scalar, I just multiply the components by that scalar. And the scalar will always be a real number, so no imaginary numbers, complex numbers, or anything to worry about. All right, so let's get into a little bit of practice here. So go ahead and maybe pause the video here and go ahead and do these calculations on your own. And so we'll go ahead and jump into these as well, make some dividers here. All right, so u plus 4v, well, that's going to be 2, 3 plus, well, 4 times v is simply the vector v multiplied by 4, which is going to be negative 4 comma 16. So it's going to be 4 times longer in length in its horizontal and vertical components. But the sign does carry over here. And then we can just add them together. So we'll have 2 minus 4 and 3 plus 16, which gives us the vector negative 2 comma 19. Now note we could also write this as negative 2i plus 19j if we were using unit vectors. Component form doesn't seem useful here with the theta, though, because we don't know the angle between them. It's probably going to be a bit messy, so we'll worry about our direction and magnitude for that last example only. Number 2, very similar to number 1, so we're going to double u, so that's going to become 4, 6, and then we're going to subtract 3v, so 3v is going to be negative 3, 12. And then this negative here does distribute. So that's going to be 4 comma 6 plus 3 comma negative 12. So I would recommend making it into an addition if you're doing subtraction by distributing the negative sign. And so we'll end up with 7 comma negative 6, it looks like. Yes. Which we could also write as 7i minus 6j if we were doing unit vector form. Number 3 is find the magnitude of u. So that's just going to be the square root of the sum of the squares. So that's just going to be radical 13. So what I'll add in here is something that we're going to be looking at in our applications, which is something called the unit vector. And what that's going to mean is it's going to be useful to think of a vector with magnitude 1, right? So if we have a vector with a particular direction with magnitude 1, that's going to allow us to do some nice multiplication later on. So the unit vector, which would be the vector of length 1 in a particular direction, can be represented by the vector u divided by its magnitude. All right, so if I take u divided by magnitude u, so in this case, our u would be 2 over rad 13 and 3 over rad 13. Then this vector is going to have a unit length 1, but it's the same direction as our original vector u. So you might say, well, how do we know that that unit length is 1? Well, we can take the magnitude of the vector. So if I take my unit vector and calculate its magnitude, that's going to be 2 over rad 13 squared plus, 3 over rad 13 squared, which is the square root of, well, we'll get 4 plus 9 over 13, which is 13 over 13, which just gives us the square root of 1. So whenever we take a vector and divide it by its own magnitude, its length will become 1. So these unit vectors are going to be useful, especially when we get to the dot product. So something to maybe file away there for next time. So let's go ahead and take a vector and find its direction and magnitude. So we've got this vector r. So we'll start maybe with the easiest calculation, which will be the magnitude. So it's going to be the sum of the squares square rooted using the Pythagorean theorem. But note, negative signs don't matter. So we actually get the same magnitude that we would get for u, since r is actually just the opposite of u. So we get rad 13, and then theta is going to be arctan of negative 3 over negative 2, which just becomes positive. But note, we are going to have to be slightly careful with our angle measure. So go ahead and grab a calculator. And let's put arctan up 3 over 2 into our calculators. And you should get a first quadrant angle. Yes, so you should get 56.310 approximately degrees. However, this is again going to be where the geometric interpretation is going to be extremely useful. We can see that vector r is in the third quadrant. So our angle is not actually 56.31 degrees, which would be in the first quadrant. So that would be if the angle were here. But it's actually 180 degrees further. So we need to add 180, which is going to give us 236.310 degrees. Or, note, we could subtract if we wanted to. So we could have subtracted 180 degrees. And so that would give us, let's see, something less easy to calculate. Negative 123.690. So just note, you can use any coterminal angles that you want. My general recommendation, though, is going to be pick something between 0 and 360, or 0 and 2 pi if you're doing radians. All right. So we're going to look at some applications next time. So I'll go ahead and pause the video here. We'll take a quick break, and then when we come back, we'll look at those applications.